Dear student, previous class I discussed about the Faraday's first law, Faraday's second law and problem related to the Faraday's first law and second law. Now I will discuss about the electrical conductivity. Electrical conductivity. At first I will discuss about the Ohm's law. According to Ohm's law, the potential difference V is that proportional to the electrical current. So I can write according to Ohm's law, the potential difference across a conductor is directly proportional to the current flowing through it. That means more is the amount of potential difference, then more is the amount of current flowing through the conductor. Mathematically I can write V proportional to I, imply that V is equal to IR. Here V is the potential difference, I is the current, R is the resistance. If I will think about the resistance, then R is equal to V by I. We know that the unit of potential difference is volt, the unit of I is ampere. That means R is equal to volt by ampere, which is equal to ohm. Ohm is written by this symbol. This is the symbol of ohm. Next I will explain about the resistance. Resistance is an opposing force which opposes the flow of electrical current through a conductor. So I can write the inherent property by virtue of which it opposes the flow of electric current through it is called resistance. It is denoted by R. It is the same that resistance is that proportional to the length of the conductor. Resistance also in that proportional to the area of cross section. Therefore I can write resistance is that proportional to the length by area. Imply that R is equal to rho into L by A, where rho is the specific resistance, A is the area of cross section of conductor, L is the length of a conductor. The unit of R is ohm. Next I will explain about the specific resistance denoted by rho. We know that rho is equal to R A by L. This is the formula for the calculation of specific resistance. If A is equal to 1 cm square, L is equal to 1 centimeter, then the volume V is equal to 1 cm square into 1 cm is equal to 1 cm cube. Put the value of A and L in this equation, then rho is equal to R. From this it is clear that the resistance of a conductor having unit length and specific resistance. It is also defined as the resistance of a conductor which having 1 cm cube volume, is called specific resistance. Now I will find the unit of specific resistance. The unit of resistance is your ohm, unit of area is your cm square, unit of length is your centimeter. Then I can find the unit of specific resistance is your ohm into centimeter. You can also write ohm into meter. Specific resistance depends upon the nature of material of the conductor. Now I will explain about the conductance. It is denoted by C. The property of a material by virtue of which it allows the flow of electricity through it is called conductance. Conductance is the reciprocal of resistance. So we can write conductance is equal to 1 by resistance. The unit of conductance is ohm inverse, or you can write mho, or like this. Next I will explain about the specific conductance. It is denoted by K. It is the reciprocal of specific resistance, also called resistivity. Similarly, specific conductance is also called conductivity. So we can write K is equal to 1 by rho. Again we know that rho is equal to RA by L. That means we can write K is equal to 1 by RA by L. That means I can write K is equal to 1 by R into L by A. We know that 1 by R is your conductance. So we can write K is equal to C into L by A, where C is the conductance, L is the length of conductor, A is the area of cross section. Here L by A is also called cell constant. If L is equal to 1 centimeter, A is equal to 1 cm square, then V is equal to 1 cm cube, that is equal to 1 ml. Now put the value of L and A in this equation, then K is equal to C. So from this relation I can write the conductance of a conductor having unit length and unit area of cross section is called specific conductance. But in case of electrolyte, the specific conductance may be defined as the conducting power of the electrolyte having volume 1 cm³ or 1 ml. This is called specific conductance. If L by A is 1 unit, then K is equal to C. So we can also give another definition: the conducting power of an electrolyte having unit cell constant is also called specific conductance. For an electrolyte, L is the distance between the two electrodes, A is the area cross section of the conductor. Suppose I will take an electrolytic tank. Here two electrodes are present like this. This is your area of cross section. This is your said to be L value. This is L value. This is your said to be A value. Your A is the area cross section of the electrode. Your L is the distance between the two electrodes. This is for an electrolyte. The unit of specific conductance is in here. C for I can write ohm inverse, and L for centimeter, A for cm square. Finally, the unit of K is ohm inverse, cm inverse. We can also write ohm inverse, meter inverse. This is your CGS unit. This is your SI unit. Next, I will explain about the cell constant. Cell constant equal to L by A. It may be defined as the distance between two parallel electrode divide by area of cross section. This is your distance between two parallel electrodes, and this is divided by A. A means is your area of cross section of an electrode. The unit of cell constant is centimeter divided by cm square. That means centimeter inverse. Next, I will explain about the equivalent conductance. It is denoted by lambda. Suppose I will take an electrolyte. The amount of the electrolyte is your 1 gram equivalent. Suppose I will take 1 gram equivalent of an electrolyte, and the ions are produced in this electrolyte, and the conducting power of these ions is called equivalent conductance. So the equivalent conductance is defined as the equivalent conductance is defined as the conducting power of all ions produced by 1 gram equivalent of an electrolyte in a solution. This is your said to be equivalent conductance. Mathematically, equivalent conductance lambda is equal to specific conductance into V, where we can write where lambda is equal to equivalent conductance, K equal to specific conductance, V is equal to volume in ml containing 1 gram equivalent of an electrolyte. We know that lambda is equal to K into V. Again we know that normality equal to Wi equivalent mass into 1000 V in ml. According to the definition, the number of equivalent mass is equal to 1. Here Wi denotes the number of equivalent mass. So here Wi is equal to 1. That means N is equal to 1000 by V in ml. Now I can find V is equal to 1000 by N. Now put this V value in this equation. Then I can write lambda is equal to K into 1000 by N. If the concentration of the solution is N gram equivalent per liter, then the volume of the solution containing 1 gram equivalent will be 1000 by N. So here I can write 1000 by N instead of V. Suppose I want to find out the unit of equivalent conductance. The unit of specific conductance is your ohm inverse into centimeter inverse. The unit of V is your cm cube. According to the definition, equivalent conductance deals with the gram equivalent. So here I can write per gram equivalent. That means I can write ohm inverse cm square into gram equivalent inverse. This is the unit of equivalent conductance. Next I will explain about the molar conductance. It is denoted by mu. Suppose I will take an electrolyte. The electrolyte having amount is 1 gram mole. That means I will take 1 gram mole of an electrolyte and the ions are produced, and the conducting power of these ions are called molar conductance. So I can write the molar conductance. The molar conductance is defined as the conducting power of all ions produced by 1 gram mole of an electrolyte. Mathematically mu is equal to K into V. Here mu equal to molar conductance, V equal to volume in ml containing 1 gram mole of electrolyte. Here K is equal to specific conductance. specific conductance. We know that molarity, that is your capital M, equal to W by molecular mass into 1000 V in ml. According to the definition, here 1 gram mole is taken, that means W by mm equal to 1, because W by mm gives the number of mole. Here the number of mole is your 1, so I can write W by mm is equal to 1. Now I can write m is equal to 1000 by V in ml, imply that V equal to 1000 by capital M. Now put the value of V here, then I can write mu equal to K into 1000 by M. So I can write if the concentration of the solution is m gram mole per liter, then the volume of the solution containing 1 gram mole will be 1000 by m. Now I want to find the unit of molar conductance. The unit of K is your
ohm inverse, centimeter inverse.
The unit of V is your cm according to definition. This is only for gram per mole, so I can write here per gram mole. That means I can write the unit of mu equal to
ohm inverse cm square into gram mole inverse.
Remember a relation between molar conductance and equivalent conductance. Molar conductance by equivalent conductance equal to normality by molarity equal to molecular mass divided by equivalent mass equal to equivalent mass into m factor divided by equivalent mass. Now cancel equivalent mass, then I can write molar conductance equal to m factor into equivalent conductance. Remember this formula. As a result, we can solve many problems related to the relation between molar conductance and equivalent conductance. Now I will solve some problem related to the equivalent conductance, molar conductance and specific conductance like this.
Now I will solve the problem number 1. The molar conductance of a solution of AlCl3 is found to be 130 mho into cm square into gram mole inverse at 298 Kelvin. What would be its equivalent conductance at the same temperature?
Here molar conductance is given, that is mu equal to 130 mho cm square gram mole inverse. Our aim to find out the equivalent conductance. In this problem, the solution is given, that is your AlCl3. When AlCl3 undergoes dissociation, it gives Al3 plus 3Cl minus. So here n factor equal to 3. We know that mu equal to n factor into equivalent conductance. Now here mu is given, that is 130 equal to n factor is your 3, that is your 130 equal to 3 into lambda. Next is your lambda is equal to 130 divided by 3 equal to 43.33 ohm inverse cm square gram equivalent inverse. Therefore, equivalent conductance equal to 43.33 ohm inverse n square gram equivalent inverse. Now I will do problem number 2. In a conductivity cell 0.01 and KCl solution having resistance 225 ohm, while 0.01 and solution of HCl having resistance 77 ohm. Specific conductance of KCl solution is 0.0014 ohm inverse centimeter inverse. Calculate the specific and equivalent conductance of the HCl solution. Look at that the KCl solution and the HCl solution is taken in a fixed conductivity cell. So the cell constant for KCl solution is equal to the cell constant for HCl solution. Here specific conductance for KCl solution is given, that is 0.0014 ohm inverse centimeter inverse. Resistance of KCl solution is also given, that is 225 ohm. We know cell constant equal to specific conductance for KCl divided by conductance for KCl. Conductance equal to 1 by resistance. So I can write specific conductance for KCl into resistance for KCl. That means I can write 0.0014 into resistance for KCl equal to 225. If I will solve this, then the cell constant is equal to 0.315 centimeter inverse. Now I will find the specific conductance for HCl solution. We know that specific conductance for HCl solution equal to cell constant into conductance of HCl solution. Conductance of HCl solution is equal to 1 by resistance of HCl solution. So I can write specific conductance for HCl solution equal to cell constant divided by resistance of HCl solution. So I can write specific conductance for HCl solution equal to, your cell constant is equal to 0.315, resistance equal to 77. Here given 77 is resistance for HCl solution. By solving, I can write the specific conductance for HCl solution equal to 0.00409 ohm inverse centimeter inverse. The second question is find the equivalent conductance of HCl solution. We know that equivalent conductance for HCl solution equal to specific conductance for HCl solution into 1000 by normality. Here the normality of HCl solution is 0.01. So I can write equivalent conductance for HCl solution equal to 0.00409 into 1000 divided by 0.01. By solving, I can write equivalent conductance for HCl equal to 4.09 into 10 to the power 2 ohm inverse n square gram equivalent inverse. Our question is calculate the specific and equivalent conductance of HCl solution. So we can write specific conductance for HCl solution equal to this, that is 0.00409 ohm inverse centimeter inverse, and the equivalent conductance for HCl solution equal to, this is the equivalent conductance. So here I can write 4.09 into 10 square ohm inverse cm square gram equivalent inverse. Next I will solve the problem number 3. A decinormal solution of sodium acetate when placed between two electrodes of area 1.5 cm square and placed at a distance of 0.72 centimeter has a resistance 52.4 ohm. Calculate its specific conductance, equivalent conductance. Here A is given, that is 1.5 cm square. L is also given, that is 0.72 cm. R is given, that is 52.4 ohm. We know that specific conductance K equal to L by A into R. Put the value of A, L and R in this equation. Then I can write 0.72 divided by 1.5 into 52.4. By solving, I can write 0.0091 ohm inverse centimeter inverse. Again, we know that lambda is equal to K into 1000 by N. The value of K is 0.0091. The value of N is decinormal, means 1 by 10. Now put the value of K and N in this equation. Then I can write lambda equal to 0.0091 into 1000 divided by 1 by 10. By solving, I can write 91 ohm inverse cm square gram equivalent inverse. Our question is to calculate the specific conductance and equivalent conductance. Therefore, I can write specific conductance equal to 0.0091 ohm inverse centimeter inverse, and equivalent conductance equal to 91 ohm inverse cm square gram equivalent inverse. Next I will solve the problem number 4. Specific conductance of a 0.01 N solution of propionic acid at 25 degree centigrade is 1.410 into 10 to the minus 4 mho into centimeter inverse. Equivalent conductivity of the acid at infinite dilution is 385.6 mho into cm square into gram equivalent inverse. Calculate the degree of dissociation of the acid at a 25 degree centigrade. We know that degree of dissociation alpha equal to big lambda divided by big lambda 0. Big lambda is the equivalent conductance for a particular concentration. Big lambda 0 is the equivalent conductance at infinite dilution. At first I will find the big lambda. Big lambda equal to K into 1000 by N. Your specific conductivity is given, that is 1.410 into minus 4 into 1000 divided by the value of n is 0.01. After solving, the big lambda is equal to 14.1 ohm inverse cm square gram equivalent inverse. In question already big lambda 0 is given, that is 385.6 mho into cm square gram equivalent inverse. Now put the value of big lambda and big lambda 0 in this equation. Then degree of dissociation alpha equal to 14.1 divided by 385.6. By solving I can write 0.0366. Our question to find out the degree of dissociation. So I can write degree of dissociation equal to 0.0366. Next I will explain about the factor influencing the conductance. First factor is your nature of electrolyte. There are two types of electrolyte. One is a strong electrolyte, another is a weak electrolyte. In case of strong electrolyte, the conductance is more as compared to the weak electrolyte, because in case of strong electrolyte, the electrolyte undergoes completely dissociation, but in case of weak electrolyte, the electrolyte undergoes partial dissociation. So we can write strong electrolyte having high equivalent conductance. Similarly, weak electrolyte having low equivalent conductance. Next factor is your dilution. Dilution means addition of the solvent molecule. Suppose I will take in weak electrolyte. In case of weak electrolyte, only few amount of electrolyte undergoes dissociation, but more amount of weak electrolyte molecule present in undissociated condition. When I will add more amount of solvent molecule, then the weak electrolyte molecule undergoes dissociation. As a result, more ions are produced. Due to more ion formation, the degree of dissociation increases. As a result, the equivalent conductance and molar conductance increases. On the other hand, the volume of weak electrolyte goes on increases. As a result, the number of ions per unit volume goes on decreases. That's why the specific conductance decreases. Remember an important point: for weak electrolyte on dilution, the equivalent conductance and molar conductance increases, but the specific conductance decreases. Next factor is your temperature. If the temperature increases, then the movement of ions is more. As a result, the conductivity increases. Experimentally, it is seen that if I will increase 1 degree centigrade temperature of an electrolyte, then the conductance increases about 2%. That means the conductance of an electrolytic solution increases about 2% for every 1 degree rise in temperature. Next factor is degree of ionization. More is the degree of ionization, means more is the dissociation of the electrolyte. That means more is the ion. More is the ion, more is the conductance. So we can write more is the degree of ionization, more is the conductance. Next factor is inter-ionic attraction. If an electrolytic solution having more inter-ionic attraction, then the conductance of the electrolytic solution goes on decreases. Next is viscosity. More is the viscosity of the electrolytic solution, less is the mobility of the ions. As a result, less is the conductance. Mobility means freeness of the ions. Next is solvation. Solvation means interaction of the ions of the solute with the molecules of the solvent. More is the solvation, less is the conductivity. When there is a decrease in the mobility of ions, that means there is a decrease in the conductance of the electrolytic solution. These are the factors affecting to the conductance of an electrolytic solution.